right, good morning. Welcome to the end of week 7. So it was great. Around 9 o'clock last night, this article was posted on this popular blogging site called Engadget. And of course, this endless cycle seems to continue. Apple posts firmware version 1.1.2, goodbye jailbreak, which is referring to the fact that Apple apparently patched the hole that folks were able to take advantage of most recently to unlock their AT&T iPhones. So I thought that would make for a good story. Even better, around 1 a.m. last night, just a few hours later, this article came out. So you see here, it's arguably a losing proposition that the good guys have here. I mean, these hacks ultimately stem typically from bugs and mistakes in software. And that's perhaps a good segue as any to a quick chat about Quiz 1. So Quiz 1 by design was more challenging. And I think most of you would probably agree with us on that. And it's certainly fine if you found yourself on Wednesday, struggling through some of the problems or some of them not coming to you obviously. However, more important than that experience now, I think, is the debriefing for yourselves on your own, taking a look at the sample solutions online, because it's not terribly problematic if now, a couple days later, this weekend, you can read through those sample solutions and say to yourself, yeah, OK, now I get this, even if it didn't come to you immediately at the time. I mean, bear in mind that the quizzes collectively for the course are only worth 20% of one's final grade, and we drop the lowest of the 3. And more than anything, they're meant to be these safety checks, milestones at various points in the semester, so that frankly you guys are sort of being compelled via these artificial means to just keep pace with the course and make sure that you conceptually are on the same page as us, and so you can tackle these remaining problem sets 5, 6, and 7 without getting hung up, we hope, on some of the fundamentals, the basics that those quizzes are meant to touch upon. So those will be returned next week in lecture and/or section. We'll be grading them on Monday at our staff meeting, so grades should go online sometime by Tuesday afternoon. So any questions, logistical or otherwise? Yes? No? All right. So let's see. A couple of announcements. So problem set 4's photographs. If you haven't gone for a nice stroll, it's beautiful out today. You have until 7 p.m. to find as many of those pictures as possible. Problem set 5 spec will go out as planned tonight. Problem set 5, recall, is all about misspellings and challenging you to implement, really for the first time, not just correct code, but as well-designed code as possible toward an end of writing as efficient, as fast, an implementation of a spell checker that you can. To incentivize you further and sort of spur a bit of friendly competition, what we've set up is a big board of sorts on the course's website, whereby we have provided you guys with a program called Big Board that will essentially benchmark the code that you write for this problem set once presumably it's all working. What that will do is run a whole bunch of test files through your spell checker, count how many seconds and milliseconds it takes for various operations to complete, and then post the results. This, actually, I'll come back to in a second. What you will see then on the course's website, assuming you are successful in getting everything correct before you run it, is that you will end up on the so-called big board. Turns out right now I'm the only one there, and I'm doing really well. So I'm currently ahead. So the challenge, of course, the gauntlet we'll throw down to you is to do much better, we hope, than my actual time. So we whipped up an implementation of the spell checker. Hopefully many of you will do better than I did with this implementation. So more on that in the problem set spec. Just to put it into context, this challenge, here's the dictionary that we promised. So right now I could scroll through this line by line, but it's an awful lot of lines because there's about 148,000 words in this dictionary. And as you can see, it's structured in such a way that things are certainly alphabetical. And for words that have common variants, like absorbed, absorbing, absorber, well, I've never used that in a sentence. You'll see that things are structured in that way in this file. So all you're getting is the text file. One of the components of the project will be for you to somehow iterate over this file, word for word for word, read it into memory, RAM that is, so that you can answer queries of the form, is this a word? Is this a word? Is this a word? Because the types of inputs that we're going to pass to your program are such things as these. And certainly it should work on any inputs, but we've gone ahead and had some fun with pulling up some big text files, including the script to Austin Powers, International Man of Mystery history. There's certainly a few words that should jump out at you there. U.S. Constitution, the Grimm's fairy tales, the script to a fun Seinfeld episode with which you might soon be familiar. And these files range in size from just a few bytes, small files, to large files, like Tolstoy's War and Peace is about 3 megabytes of text in text form. So, all toward an end of spurring you toward writing more efficient code. Unlike past problem sets, this problem set will be due in 2 parts. The full thing is due as planned next Friday, but to help you help yourselves, by this Tuesday night will a design document, so to speak, be due to your teaching fellows via email. So more details on that in the spec, but this is meant to force you, frankly, for your own sake, to think about the problem a bit in advance, not necessarily writing code, but just so that you're in a good place mentally to take this on, so that you're not in the lab Thursday at night working on this thing for the first time, which, as I hope you're increasingly learning, is not a fun way to spend a Thursday night. So, any questions about that? No? All right, and finally, the final project specification, though not due for several months, will be also posted to the course's website, and we'll discuss it next week as well, so that you can begin thinking about that. All right, let me ask that you take a moment. I'm going to turn on some background music here and take out a piece of scrap paper, because what we need from you is the following. We would like you to have a bit of a retrospective here and give us some review questions yourself from these various weeks. And we don't need a huge number of questions here to reflect on how quiz 1 went. So let me arbitrarily say the following. On this scrap paper, you don't have to write your name, but we would like you to write week something, which I'll assign you in a moment, and then write a question as well as a correct answer in the category that you're assigned. And it should be a question that doesn't involve coding, but something that can be answered in a sentence or two verbally, something of that form. So let's arbitrarily say if you're in this section and sitting in these back 4 or so rows, you guys are week 0. So on your paper, write week 0 and then give us a question and ideally a correct answer. You guys in front of them will be week 1. You guys in the first 2 rows will be week 3. You guys in the back 3 rows will be week 4. Oh, well, who did I skip? 3, 4. Okay, you guys will be week 2. Okay, from here on down, and you guys are week 5. Okay, I think I exhausted week 0 through 5. So go ahead and take just a couple minutes and give us a question and an answer from your assigned week. Any of those categories. They're just meant to give you hints as to what we covered in those weeks. Make them good. For those of you kind of staring blankly, we can appreciate it was hard to come up with answers on the quiz, but the questions should be easier. In a moment, can you guys help me collect these things and just keep them separated by week? Okay, you should be wrapping up your question about now, as well as your answer. Again, you don't need to put your name on it, but do write the week number. The shorter the better. And as you're done, go ahead and hand it to the appropriate teaching fellow nearest you. And we'll keep all the weeks separated properly. All right, do wrap up if you haven't already. Teaching fellows are coming around. All right. Okay. Okay. Do you mind just sorting to make sure we're okay? All right. Any papers still lingering in the audience? All right. I'll grab these and we'll move on. Thank you. Okay. Thank you. Thank you. All right, these are week 4s. All right, we'll shuffle those up or sort those in a moment. Actually, how appropriate that we're focusing on sort then. All right, so let's wrap up this one detail as we finish up over here. Yeah, okay. Okay, all right, week 2. All right, so here we left off, which was kind of a crazy picture. The motivation for Heapsort, though, to set the stage here was what exactly, right? Who cares about Heapsort? Well, that's actually a bad question to ask. It's probably no one. But if you had to care about Heapsort, why would you care about Heapsort? What? Okay, we'll go to this side of the room. Heapsort, come on. All right, I'll lead you. What was its running time for sort? So we claimed at the end of last time. So it was n log n, supposedly, but we've already seen an algorithm that's n log n. And even though we didn't dwell on implementation specifics, what was that algorithm and what was the cost of that algorithm? Yeah, so merge sort and so it takes up more memory, we said. And again, we didn't look at the implementation details, but we did claim that the cost of that performance comes in terms of space. Well, the motivation on Monday for introducing these things, heapifying complete binary trees, was to claim that we can actually sort n numbers still in n log n time, but without the need for additional space. In fact, we can do all of this in an array, it turns out, even though we're looking at things by way of a tree. So just to refresh you, here might be an arbitrary, complete binary tree. And by that, we mean all the nodes are as far up as possible and as far to the left as possible. But beyond that, they're pretty much randomly arranged in terms of the values in each node. We went about heapifying this thing, thanks guys, in order to turn it into this thing known as a heap. And there's one key property that's missing in the top left graph. I mean, what's the goal of turning, what is a heap besides complete? Yeah. Okay, not quite, not quite. That's more of a binary search tree, but it's the right spirit. So it's also balanced. So that too, not quite, that's not necessarily the case. All that's required is that if there are leaves in the tree, that they're as high up as possible, as far to the left, but it would still be a heap if we even removed the number 6 at the end there and then got rid of that right child. But there is one property that's necessary for something to be a heap. Yeah. Perfect. So that's the one that is germane to a heap. So the children are smaller values than the parents. So by this logic, recursively, what node should be at the very top of a heap? All right, so the largest value should be at the very top of the tree, the so-called root. And that's something we can exploit. So the means by which we take a completely arbitrary but complete binary tree was to heapify it step by step by step. And essentially the algorithm is as follows. We start at the bottommost rightmost leaf node, and we heapify that node. Well, fortunately, if the subtree we're looking at is just the node 6, it's already a heap. Right? It's just a root node. It has no children, so we're done. So conceptually, we can repeat that now, moving to the left. 7 is now heapified. Now let's move up and start at the right, sort of like a typewriter returning to the end of a line. So now we'll heapify 3. Well, that's quite easy to do. We'll heapify 9. That's easy to do. 4, easy to do. And now things are getting more interesting. And this is where we began our story last time. So now we have a subtree whose root is 2. Is that subtree a heap itself? No, because clearly 7 should be switched with 2. And so we quote unquote heapified that tree. All right, and now we repeated. We kept going to the left and up, which brings us now to this subtree, starting with 8. This 2 needed to be heapified, so we swapped 9 with 8. And then we continued to the left. And then we went back to the top and moved to the left again until finally we got to the top of that tree. And in the end, the net effect is that the whole thing is heapified, so to speak. So the question we landed with on Monday is, how long did that take? Well, according to this algorithm, how many subtrees are we considering in total? So n, right? I just iteratively went through every node in the tree, and in each iteration, I suppose that that node represented the root of some subtree. Some of them were kind of silly because they were just single nodes, but that's a subtree of size 1. But then things got more interesting. Now the question is, we're clearly doing something n times. How much does it cost us to heapify each of those subtrees? Well, what's the maximum height of any of these subtrees, given the definition of a complete binary tree? If you've got n nodes and you arrange them in this binary tree that's complete, how tall is the tree mathematically? So it's log n. So what that means is that on each iteration, we're heapifying a little subtree. But that subtree can be no more than log n in height, which is to say that even in the worst case, if we're considering this big complete binary tree, in the worst case, we might have to bubble up some element, or bubble up some small element from the top all the way down to the leaf node. So an element might have to move a total of log n steps, which is log n steps for us in terms of cost. So in the end, we're doing something n times, and each of those n things takes us maximally log n steps. And so how long does it take to heapify a tree like this? N log n. Yeah? So it's a good question. Can this bubbling process, for instance, at the very end, when we have the number 1 at the top, which is clearly in the wrong place, he needs to now bubble down all the way to the bottom, it seems. But so long as you choose the correct child to swap that parent with, you shouldn't mess things up because we've built things from the bottom up. In fact, there's no way to break that algorithm if you've done it stepwise from the bottom on up as we have. So it's a good thought, but it's handled inherently by that process. We could goof, though, if in this top node, we didn't just take 1 and 9, but rather swapped 1 and 7. Then things would start to get messy. But we handled that last time. Other questions? All right, so the who cares question. Well, if we have now this sort of building block, we can actually sort numbers, just as we've been doing, but now we can do it more efficiently. So suppose, for discussion's sake, that the list of numbers that we're given to sort is 35, 15, 77, and so forth in that order. So some pseudo-random order. If I want to heapify those numbers, conceptually what I can do is I can drop them into a complete binary tree in that order, top to bottom, left to right, 35, 15, 17, 60, 22, and so forth. And that's exactly the order that I've dropped them into this complete binary tree. Now I claim that if I heapify this tree and then start popping the root elements off one at a time, what I'm going to get in the end is a sorted list, effectively in reverse order, by grabbing the biggest element every time, which we said is at the top of this tree. So how does this work? Well, here's our complete arbitrary binary tree up here. And so I go ahead and heapify it using the steps we just discussed. So between A and B, we've heapified the tree. So now the biggest element, as you would hope, is at the very top of the tree, the so-called root element. And now I claim that to begin sorting this list, I can pluck the root element from this tree and just swap it with the bottommost rightmost leaf node. And I don't care what its value is. I know it's smaller, but I'm going to put it at the very bottom of this tree. Now I've screwed up the heap, right? Because now who's at the top accordingly? So 35. But the idea is that now effectively think of us as just chopping that bottommost leaf off, 77, and putting it at the end of our array. Right, just so mentally tuck it away and remove that node. Now there's a problem though. This tree, even once I've removed 77, is no longer a heap. What must I do? So I need to swap. So the question then is, worst case, how many swaps am I going to have to do? But this is just like that last step of the previous example where I had to heapify an almost heap, where there was just one guy who was out of order, and I needed to bubble him down to the left or down to the right all the way until the procedure should stop. Well, in this case, 35 should be swapped first with whom in the top right picture? 60, because that's the bigger of the children. And now we have 35 as a left child of 60. Do we need to bubble it down further? No, but in the worst case, how many steps would that reheapification have taken? Just log n. OK, so I plucked off one node. It cost me log n steps. So we seem to be OK now. Now let's repeat. Who's at the top of the root by definition? The top of the tree. The biggest element, the next biggest element. So let's go ahead too and now pluck 60 out of the root, swap him with the bottommost rightmost node, effectively severing that leaf from the tree, so that now at the end of our list we have 77 in place and 60 in place. And if we're using an array, this is fine too. We can just use the end of the elements. And we'll see how this works in a moment. And now I can repeat. So if you buy the fact that fixing the tree on each step requires no more than log n steps, well, how many steps does it take total to sort a list of numbers using Heapsort? So it's n log n, right? There's this startup cost, to be sure, of n log n steps just to do what in step 1? Heapify the whole darn thing, because originally it's completely arbitrary. Everything's randomly sorted. So this comes at a cost. And then after that, it takes us, we have to pluck off n root nodes. But each time we do that, we screw up the heap, and we need to fix it. So each of those fixes takes, you said, log n steps. So that's another log n steps to sort the list. But asymptotically, this just equals n log n, because we said we throw away constants. So again, for large values now, the claim is that heap sort is as sufficient, at least asymptotically, as merge sort. But it turns out we can get away with doing this all with the memory we're given. And by that, I mean the following. How can you go about representing a tree in memory? Well, with problem set 6, you're going to do this with literally pointers. And you're going to create essentially a linked list, but that looks like a tree, using pointers for the children, as we discussed on the board on Monday. But it turns out that if you use a complete binary tree, you can actually represent those things in arrays. That is to say, I can represent that top left tree as follows: 35, 15, 77, 60, 22, and 41. I said that I was given these numbers as an array, and it turns out even though I've been drawing them as a tree, I can actually leave them in the array that I was given for the following reason. Because these things are ordered from top to bottom as far to the left as possible in satisfying the so-called completeness property, well, this is node 0, 1, 2, 3, 4, 5. And it turns out that if a node's index is I, what's the index of his left child mathematically? You can sort of figure it out just by guessing and checking. We'll do 0 indexing. What's a quick little formula that gives us his left child? So let's take an example. Here's the root node, 0. His left child is supposed to be this guy. So it turns out that that should do it, right? So 2i plus 1. So it's 2 times 0 plus 1 gives us 1. That gives us the left child. If I then say that the right child, odds are, is going to be right next to it, 2i plus 2. Let's see if that works. So 2 times 0 plus 2 does, in fact, give me the right child. All right, that's fine and good for the first few. Now let's try another one. What about 15? So 15 when I equals 1. So 2 times 1 is 2. Plus 1 is 3, so that's 0, 1, 2, 3. 60 appears. Whew, it's the left child. And if we plus 2 instead, we're going to get the right child. So the reason for revealing this is that even though it looks like a huge amount of overhead just to get some numbers sorted, turns out you can do it all within the memory you're given. And that's in stark contrast to merge sort, which especially for really large inputs, really large arrays, you need twice as much space typically. Though there are little hacks you can do to chip away at that, but you do need more space. And this is in general a neat technique when conceptually you can view problems in a form that's better suited for thinking about them, but underneath the hood you can actually implement them very efficiently with random access and arrays and these fundamentals. So any questions about heap sort? No? All right, so we thought we would wind down a bit from quiz 1, especially since you're feeling a little uncomfortable. And it turns out we have a whole lot of questions here. We also have a whole lot of chairs. So I'm going to need a few volunteers to sign away their level of comfort and come on down here. I got one. Come on down. Need another. 2. Come on down. Karen. Why don't you guys start over here and start thinking of, we'll call it a team name, if you will. All right, I need 2 more students. Come on, these guys volunteered pretty quickly. Pretty fast. Don't make eye contact with me. Come on, 2 more students. OK, come on down. What's your name again? Chris. Come on down, Chris. And who's going to save Chris the awkwardness of being on his own here? Come on. Whoa, 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 whoa. You OK?
Yeah, I'm OK.
OK, that could not be more awkward then. All right. Come on, please, someone help Chris out now. OK, come on down. That worked. OK. All right, come on down. What's your name? OK, come on down. Thank you. And now I need 3 more. How about these guys? All right. So turns out we have some nice questions here. We tried to make this a bit of a leading setup. Here's what we've got here. What we're about to do, if you will, is a little of this. So that's what you've just signed yourselves up for. We got a little more animation. Yeah, that'll be me. All right, so here we go. We've got a bunch of questions here to keep me sane. We're not going to do this in pose and answer, ask a question form. So rather, instead, we're going to just do questions and answers, which you guys, the audience, were so kind to put together for us. But you can see that we do, in fact, have 2 mics down there, which should pick up. One of you guys is on the cord. OK. All right, so we'll have this lined up. Those guys are now mic'd. And to help take the edge, then, if you will, off of quiz 1, it's going to be a long game. All right. I'm going to try to keep myself as sane as possible here. 5, that's week 5. This is week 4. This is week 3, 2, 1, and 0 will keep up here. All right, so here we go. As you might expect, we have a few different categories here. Turns out they perfectly correlate with the categories we gave you guys. I'm going to need 1 more volunteer. It's a non-speaking role, but you have to be good at adding numbers like those together. Think of this as a sort of Vanna White meets Jeopardy kind of role. So you get this piece of chalk. Who's good at math? Yeah, come on down. All right, what's your name? Nathan. Nathan, come on down. All right, so Nathan, if you will, we're going to have to keep track of these guys somehow with their names and their scores. So you're going to be running the board for us, if you don't mind. What name have you guys decided on?
Team Absorber.
That's great. You used it in a sentence. That's good. See, we even have effects. That's good. All right. Middle team, what would your name be?
The Trippers.
The Trippers. How appropriate. Chris is OK with that? OK. All right. And the teaching fellows, what will it be?
Lemming.
What is that?
Lemming.
Lemming. All right, lemming. All right, so before this began, we tossed a coin. Chris won the toss, so Chris is going to begin, I think, in fairness. So Chris, you're going to go ahead and pick a category. I'll choose the question, and then anyone can buzz in, so to speak. We clearly don't have buzzers, so we're going to go with a show of hands, and Nathan's going to ultimately be our judge. So he'll call on whoever's hand goes up first. All right, or point, since I promised it's a non-speaking role. All right, Chris, what category would you like?
Week 2.
Week 2. So in week 2, the question for anyone, again, raise your hand as this comes up. Explain why a Vigenère cipher is harder to crack by trial and error than a Caesar cipher. Yes. Absorbers. It doesn't need to be a formal statement. It's oh, I'm sorry. Actually, how much is this going to be for? A low number.
It's going to be 200.
This is for 200. Good. I forgot the rules there. Okay, go ahead, absorbers.
All right. The key changes with different letters, so it's harder to do with a Caesar cipher. Once you figure out the letter, you've cracked it. With the Vigenère, you've got to do harder statistical analysis if you're trying to do that.
All right, audience, what do you think? Yeah? Okay, that's great. Okay. All right, 200. So you guys are in control. What would you like?
I will do week 0 for 1,000.
Week 0 for 1,000. All right, remember that any of you guys can buzz in. So what is the largest decimal number that you can store with 8 bits? Okay, the trippers?
255.
To audience? Yes, for $1,000. And you guys take the lead. All right, Chris and the trippers, what would you like? Category and point-wise.
Week 1 for 1,000.
Week 1 for 1,000. So your question here is going to be, what? Ooh, all right, that's worth 1,000. What type does malloc return by default? Oh, teaching fellows.
Void star.
Audience? Yes, all right, excellent, for 1,000. So we're currently tied at 1,000, 200. But you were good for buzzing in fast. So TFs, you're in control. What do you want?
Week 2 for 1,000.
Apparently. Yeah, did we get to that in week 1? All right. Yeah, that says week 1, so whoever's handwriting this is. All right, anyhow, what do you got, TFs?
A week 2 for 1,000?
Week 2 for 1,000. So in week 2, your question is going to be, what are the benefits of using a global variable, and what are the drawbacks? Absorbers.
Benefit, you can get it in any function. The drawback is pretty much the same. You can get in any function. It's inelegant. It's kind of silly.
Well, apparently the answer is your TF will hate it because it often means the same variable has different values within the program. But you wanted to give it to him? All right, $1,000. You're in the lead. What would you guys like, absorbers?
Week 3 for 1,000. Week
3 for $1,000. Okay, your question is from week 3. What? Just trying to be a little selective here. All right. How about what? Okay. What? All right. Not only is there no answer, what is the difference between selection and binary and bubble sort? Selection and bubble sort. Again.
Bubble sort, you iterate through n times and switch any 2 values that are out of order.
Okay.
Selection and sort.
I guess you're on this one, Karen.
I knew bubble sort.
With the selection sort, you look at the end of the rest of the list and you find the smallest value that's ahead of you. You stick it where you are, then you move on to the next place, find the smallest number remaining, stick it where you are, and move along.
You have to convince them. So what do you guys think? All right, very good. All right. That was pathetic clapping. Okay. All right, you guys are still in control. 2,200 versus the other 2 guys. What do you want?
Week 4 for 1,000.
Week 4 for 1,000. This is our last $1,000 category. Your question is going to be, what is... Wow. Okay, how about what is the purpose of memoization? Karen, hesitant though you were there.
Memoization is you're going to an algorithm that keeps like particularly for a recursive one, you want to be able to store any numbers that you've got from previous iterations, so you don't have to keep getting them over and over and over and over again.
I'm convinced. All right, excellent for 1,000. So these guys are really pulling ahead. Let's see if maybe we can call on someone else next time. So go ahead and choose your category. Got another one, time for one or more questions in single Jeopardy here.
Week 0 for 800.
Week 0 for $800. All right, week 0. And your question is going to be, okay, fine, we'll do it. This one involves code. So if x equals 0, a equals 1, what's wrong with the above? What is it? The trippers, okay.
Setting x to 0 instead of asking if x is equal to 0.
Okay, what?
So there's no semicolon after the 1.
There's no. Oh, yeah, that's just minus 800 over here. Okay, so we'll give it to him for $800. Sure. That was pretty weak, whoever. Okay. No, it's okay. We're not judging. All right. All right, time for one more question in this round. What do you guys want?
Week 1 for 800.
Week 1 for $800. Your question is going to be from week 1. It's likely about pointers and dynamic memory allocation. Why would someone use a do-while loop? TFs?
If you want to go through the loop at least one time and then check your condition.
Audience? All right, excellent. Oh. All right, so that's good. It's tied at 1,800, 1,800, 3,200. Why don't we go ahead and pause for a moment before moving on to Double Jeopardy here and give our contestants a chance to introduce themselves. So, Karen, would you like to say something about yourself?
I'm a sophomore in Dunster House, which rocks. Dunster House is awesome. And
all right, moving on. Go ahead.
I'm Matt. I live off campus. I'm a junior. My favorite primitive memory variable type would be an integer.
Oh, very nice. All right. Chris, would you like to introduce yourself again?
I'm a freshman. I'm in Strauss.
Excellent. All right.
My name is Tim. I'm a sophomore at Courier.
Sophomore in Courier, all right. And the Teaching Fellows teams. A little something interesting about each of you, since we know who you are.
Okay. Put me on the spot. I don't know.
What?
That's fantastic. And I will say, David Haley has this weird distinction of being the only one I know of to have that George Costanza poster in his dorm room. So as I understand things, people have been trying to get into his room all week to take a photo. All right, so we've got time for a few more questions here. Double Jeopardy. We've doubled all of the point values. The categories now are week 1 through 5. We're going to go ahead and let the Teaching Fellows choose the category first. What would you guys like?
Week 5 for 2,000.
Week 5 for $2,000. We got the most questions from week 5 since I didn't sort folks evenly. So the question for you is, here we go. What does malloc return? Trippers.
Void star.
Void star is correct again for $2,000. Very nicely done. All right. Time for a couple more questions. What will you have?
Week 4 for 2,000.
Week 4 for?
2,000.
For 2,000. So week 4 for 2,000. Your question here is going to be, why is a program like better to debug? Okay. All right. Why is a program like GDB better to debug with than simply? This is a comparison question. Okay. Go ahead.
GDB would be a better tool to use oftentimes than just simply using a printf statement or something like that, because you can run through line by line and see what each of your variables is after a single thing is done, and actually check inside the program what's going on.
Very convincing. Yes? No? All right. For two. Why is GDB better than simply printfing? Which is apparently a verb, so that works too. All right, you're in control. Time for just a couple more questions here. Oh, I forgot. We actually do have lots of sound effects here, so.
First round, the Jeopardy round.
Let's use that one up. All right, we got one more for you. All right?
Week 1 for 2,000?
Week 1 for $2,000. About the last question in this category. All right, week 1 for $2,000. So your question is going to be, before we move to Final Jeopardy, your question is going to... Okay, it's funny because the answer is, I honestly don't know. I saw the word on the list and wanted to know. So the question is, what does associativity mean? Okay, so no one got that. Associativity? Someone from the audience? Yes. Right, so think back to that big precedence table. When things associate left to right, right to left, it means you do the addition first, the subtraction first, multiplication, those kinds of things. You're nicely done, everyone. All right, so now we move on to Final Jeopardy. Recall that in Final Jeopardy, these guys are going to choose a dollar amount to commit after seeing the topic. They have $5,200, $3,800, and $1,800. That's okay. So they were instructed to throw the game. So they can still win if you guys not so good with the Jeopardy strategy. So your category before you choose your dollar amount is computer science. So here's a piece of paper for each of you. All right, go ahead, if you will, and commit some dollar amounts less than or equal to what you have. We'll then present you with the question.
We don't have
writing.
Oh, okay, here you go. All right. And now that they've committed to their dollar amounts, we're going to go ahead and reveal the question. So your question is, for which you'll have a limited amount of time to write your answer, is the following. Decrypt this. All right, jot down anything. All right, so the teaching fellows were by instruction in third place at $1,800. They wagered $1,800 in hexadecimal. And their answer is PBEERBG. Okay, not correct, but let's move on to the trippers who were in second place, who wagered $3,800, also in hexadecimal. That's not hexadecimal. Yeah, is that what we're getting at?
What? No, our bet was in hexadecimal.
Oh, the bet is in hexadecimal. Okay, so were these guys. All right, unfortunately, the answer there was blank. That's fine. So we're turned to our last group here, the absorbers, who wagered $2,400 and won. And look at this. They do deserve the round of applause. The answer is, in fact, correct. So a big round of applause here for the absorbers and all of our contestants. We will return quiz 1 to you next week. Have a good weekend. Do you mind?